In the previous video, we explored distance-time graphs, which help us understand how the distance traveled by an object changes over time. In today's video, however, our focus shifts to velocity-time graphs, which illustrate how an object's velocity varies as time progresses. Although these two types of graphs may appear quite similar at first glance, it is very easy to confuse them, especially in an exam setting. Therefore, it is important to pay close attention and double-check which graph you're dealing with. In a velocity-time graph, velocity is shown on the vertical axis, also known as the y-axis, while time is displayed on the horizontal axis, or the x-axis. To determine the gradient, or slope, of the curve at any given point, we need to calculate the change in velocity divided by the change in time. This should sound familiar, because it is the exact formula used to calculate acceleration. So, whenever you look at a velocity-time graph, remember that the gradient always tells you the acceleration of the object. This means that if the curve shows a constant positive gradient, like it does in the initial section of the graph, the object must be experiencing constant acceleration. On the other hand, if the curve shows a consistent negative gradient, such as the one in the final section, this indicates that the object is undergoing constant deceleration, meaning its speed is steadily decreasing. To calculate acceleration or deceleration, we can simply substitute the appropriate values into our formula. For instance, in the first section of the graph, if the change in velocity is 3 meters per second and the change in time is 2 seconds, then the acceleration is 3 divided by 2, which gives us 1.5 meters per second squared. When we observe flat or horizontal sections of the graph, the gradient is 0. This tells us that there is no acceleration taking place, which means the object's velocity is constant during this period. It is neither increasing nor decreasing. To determine the velocity during these stages, we simply refer to the y-axis. In the second segment of the graph, for example, the velocity is 3 meters per second, and in the fourth segment, it is 5 meters per second. If the curve begins to steepen like in the third segment, it indicates that the gradient is increasing. This means that the rate of acceleration is also increasing, and the object is speeding up at a faster rate over time. Now, let's talk about how to find the distance traveled from a velocity-time graph. Unlike a distance-time graph where distance is read directly from the y-axis, here we calculate distance by finding the area under the curve. For example, if we want to find out how far an object has traveled in the first 4 seconds, we would look at the area under the graph within that time interval. To make this calculation easier, we can split the area into simpler geometric shapes such as a triangle and a rectangle. The formula for the area of a triangle is 1/2 multiplied by the base multiplied by the height. In this case, that would be 1/2 times 2, which is the time, multiplied by 3, which is the velocity, giving us an area of 3 meters. Next, we calculate the area of the rectangle by multiplying its base and height, which in this case is 2 times 3, resulting in 6 meters. Adding these two areas together, we find that the total area under the graph for the first 4 seconds is 3 plus 6, which equals 9 meters. This means the object has traveled 9 meters during this time. Now, although area is usually expressed in square meters, in this context we are finding distance, so the result is simply given in meters. This is one of those special cases where we do not use the standard unit for area, and it's something you just have to accept and remember. Calculating the area under curved parts of the graph is a bit more complex. If an estimate is acceptable, the graph will typically be printed over a grid background. This makes it easier to estimate the area by counting the number of grid squares under the curve. For example, in a graph where each square represents 1 meter of distance traveled, we can count the full and partial squares under a curved section. Suppose we have 6 full squares, 1 that is almost full, and 2 that are about half full. We can approximate the 2 half squares as 1 whole square. When we add all these together, we get approximately 8 full squares. So, the total distance traveled during this 2-second period would be about 8 meters. That wraps up everything we wanted to cover in this video. If you found it useful, please consider telling your friends and your teachers about our content. We appreciate your support and look forward to seeing you in the next video.